video is all about calculations of electrochemical cells made by metals, and you're going to encounter the basic concepts for corrosion. When we say corrosion, it is actually the oxidation, degradation of metals. Okay? And the rightful term for iron corrosion is rust. Okay, for other metals, say for example, the corrosion of copper, corrosion of silver. Okay, the rightful term for those is just corrosion, not rust. Okay, the rust is only applicable for the corrosion of iron. Okay, I repeat, rust is only applied for the oxidation corrosion of iron. When we say oxidation, it is actually the loss of electrons of particularly metals for this topic. Now let's proceed. Now, on the laboratory scale, okay, so this is actually the design of chemists, electrical engineers, and chemical engineers for battery. Okay, they're going to encounter anode and cathode. Okay, for a battery, okay, so we have the anode side. When we say the anode side, it is the negative pole of a battery. And for the protruding sides of a battery, for cars, battery of clocks, watches, the protruding side is called cathode. So the protruding side of a battery is actually positive. Now, what happens into the anode? Okay. So since the anode is the negative pole of a battery, the reaction occurs on the anode is oxidation. Okay. For the cathode part, this is the positive pole of the battery. As said earlier, reduction occurs. Now, to balance the following oxidation half-cell reaction for this anode pole, say for example, we have an elemental B. Okay? This is not boron. This is just an elemental B, okay? Hypothetical B. Now, since this letter B here has no positive nor negative sign, this is an elemental B with a charge 0. So B now converts to B positive. Okay, so this is oxidized to be positive. Now, to balance the whole equation, when we say oxidation, it is the loss of electrons. Okay, now let's focus on the product side of this oxidation half-cell reaction. Now, since B here has a charge of positive, or this is positive 1, to balance the whole equation, since B here is 0 on charges, we need to add a single negatively charged particle here as electron so that positive 1 plus negative 1 will yield as a charge for B for the product as 0. All right? So this is already a balanced equation. Now let's proceed with the reduction half-cell reaction. Now, say for example, we have an elemental A with a positive charge as positive 1. And then this is reduced to A. Okay? When we say reduction, it is the gain of electrons of the reactant side. Now, from positive, since this is plus 1, and our product A here has no charge or 0 charge. To balance the whole equation, this is positive 1. Okay, so where are we going to add our electrons? When we say electron, it is negatively charged. So it has a symbol of E negative. Okay, so since this is positive 1, this is negative 1. Okay, so this zeroes out for the charge of A. Now, let's proceed with the net reaction. For the net reaction, we're just going to add both half-cell reactions, namely as oxidation cell and reduction cell. Okay, the reactions here. So B plus A plus, forming the products of A plus B plus. Okay. Now this cancels out the electrons. Okay. So earlier, on my previous videos for electrochemical cells, the N now there is the number of electrons that has been canceled out in a half cell reaction, or it is the same with the transferred electrons on this battery. So N now here is equal to 1 mole electron. Now let's define again cathode. Now cathode is where reduction occurs. Okay, our electrons are consumed on this side. Okay? When we say reduction, it is the gain of electrons at the reactant part. Now for the anode, anode now is the electrode where oxidation occurs. This is where electrons are also produced. Okay? Now, when we say Nernst equation, if we have encountered this reaction as the oxidation element or oxidation ion plus the number of electrons, okay, forming reduction. Now we're going to use this following equation. Our cell voltage is equal to standard voltage plus gas constant multiplied with temperature all over the number of electrons that canceled out in a half cell reaction multiplied with the Faraday's constant times the natural logarithm of AO. AO is the concentration at the oxidation cell all over AR. AR is the concentration of the reduction cell. Okay. Now, again, these are the variables represented by this equation. E is the cell voltage, E naught is the standard voltage, R is the gas constant. For SI units, we're going to use this one as 8.314 joule per mole Kelvin, or this is also equal to kilojoule per kilomole Kelvin. N is the redox electrons that canceled out or transferred within this battery. And F is the Faraday's constant at 9.648 times 10 raised to 4 joule per mole volts. AO now is the concentration of the oxidation cell as said earlier. And AR is the concentration of reduction cell. Okay, so we have another equation as Gibbs Helmholtz equation. Delta G naught is equal to delta H naught minus the following product quantity as temperature or T multiplied with delta S naught. And then again, we're going to encounter this as delta G is equal to negative N times F times E naught. Okay, let's define the following variables. Delta G is the Gibbs free energy as kilojoules. T is temperature in Kelvin for SI units. And delta H naught is the enthalpy of the half cell reaction. Okay, this must be in kilojoules. And delta S naught is the entropy in kilojoule per Kelvin. When we say entropy, it is the degree of disorderliness. Again, the degree of disorderliness. And we have F, Faraday's constant at 9.648 times 10. This must be raised to 4 joule per mole volts. And we have N as the moles of metals in balance reaction transferred or canceled out. Okay. Now we have the table for standard reduction potentials at 25 degrees Celsius. Now this is very useful for solving for this standard voltage as the reduction voltage plus oxidation voltage. So we're going to encounter this on our calculation later. So my next video is all about calculations of electrochemical cells with the use of metals. Okay.